We welcome Mr. S.P. Brahmaiah. It is our pleasure to introduce Mr. S.P. Brahmaiah, who is working as an executive engineer at Xylem Water Solutions again, but in the Bangalore office. Sir is currently pursuing MTech from Data Science and Artificial Intelligence from PES University and hold a BTech degree in Electronics and Communication. Sir is having more than 18 years of experience in embedded products, with the last 16 plus years focused on the design, development, and implementation of embedded systems using microcontrollers and FPGAs. Additionally, Sir has extensively experience in design, development, and successful implementation of cryptography and network security systems. His work involves hardware design, firmware development for embedded product, custom application testing, preparation of test cases in embedded domain. Such area is expertise in embedded system design, IoT solutions, PDLC, that is product development life cycle, implementation of embedded project life cycles, embedded develop ops and R&D activities. Sir is also skilled with machine learning, deep learning, and generative AI and applying them to the embedded domain. So, sir is vastly experienced, and I believe that this session will greatly help those who are pursuing research and those who are interested in the AI ML applications in specifically embedded domain. So, we welcome Mr. Brahmaiah. Sir, you may start your presentation, sir.
Yeah, thank you.
Yes, sir.
Thank you for the, highlights. So, is that presentation visible?
Yes, it is visible. Yeah.
Yeah, okay. So, good evening, everyone. Myself, Brahmaiah. Today, we will explore how artificial intelligence and machine learning are transforming traditional IoT systems into intelligent self-learning systems. I think most of the people knows IoT, the it's Internet of Things. So this IoT has already connected billions of devices worldwide. However, connectivity alone is no longer sufficient. By integrating AML, IoT devices can analyze data, make predictions, and take autonomous decisions in real time. So this session focuses on how AML enhances IoT devices, the architectures involved, real world application across industries, and measurable business value derived from these technologies. So whether you are from engineering, research, industry, or academia, this presentation will give you both technical insights and strategic understanding of AML driven IoT systems. So let's begin with the presentation agenda and learning objectives, which will outline what we'll cover today. So this slide outlines the overall structure of today's presentation, helping you to understand how the discussion will progress from fundamentals to real world impact. We will start with an executive summary and market landscape to understand why AML enabled IoT is gaining momentum. Then we will move into technical foundations and system architecture, explaining how AI models are deployed at the edge and in the cloud. So after that, we will explore industry specific applications followed by implementation frameworks, tools and platforms. So we will also review real world case studies and ROA analysis, return on investment analysis, and finally discuss future trends and strategic recommendations. So by the end of this presentation, you should be able to identify where and how AML can be integrated into IoT systems, understand edge versus cloud processing trade-off, recognize sector-specific benefits of AI-powered IoT, applying best practices for implementation of AML, and develop a high-level strategic roadmap for AML IoT adoption. So these learning objectives are designed to ensure you gain both conceptual clarity and practical insights, not just theoretical knowledge. So with this roadmap in mind, let's move on to executive summary and market overview to understand the current growth and adoption trends. So this slide gives a high-level executive view of AML powered IoT market, highlighting why organizations across industries are rapidly adopting these technologies. The AIoT market, nothing but the artificial Internet of Things. So right now I am using AIoT for short name. So it's nothing but the artificial Internet of Things. The AIoT market is projected to reach 16.2 billion by 2025, representing nearly 290% growth. This shows that AI integration is becoming a core capability. It is not an optional enhancement for IoT systems. Around 75% IoT devices are expected to use AML in some form, whether for prediction, automation, or intelligent decision making. From a return investment perspective, organizations are seeing an average return on investment between 250% and 400%, which strongly justifies investment. The several factors for accelerating this growth, the 5G rollout, enabling ultra low latency communication and maturity of the edge computing, allowing local AI processing, the advances in AI specific chips, making inference faster and energy efficient, and the overall push for digital transformation across industries. See, the cloud-based AI remains dominant with 92% adoption, but Edge AI is already adopted at 78%, including a clear shift between real-time and on-device intelligence. Interestingly, the hybrid approach lead at 85%, showing that the most enterprises combine both edge and cloud for optimal performance. The key message here is that the AML in IoT is no longer experimental, and that is proven value and generating technology across all the sectors. And we can see the average return on investment by application. The predictive maintenance is gaining more as I mean uh, basically to avoid the equipment failures. So these are the the IoT strategies are applied on this predictive maintenance to avoid this one, and so that the return on investment will be more for the predictive maintenance. And the next is the supply chain. So later it followed for other application based areas. So let's look at how AML is technically integrated into IoT systems through layered architecture. So this actually gives the slide overview of how AML is used for our. It's actually a combination. I mean, as you can see in the figure, this slide illustrates how AML. I mean, end to end. We call it as end to end. So it will be able to understand like the end to end AML enabled IoT systems, showing how the intelligence flows from devices at the bottom to cloud AI platforms at the top. So from the let's start. Understanding from the bottom layer, the IoT devices. So at the bottom, we have diverse IoT devices, including sensors, actuators, and for the data collection and control, the smart devices like home appliances, the wearable devices for healthy and active monitoring, industrial equipment used in the factories, and autonomous vehicle which are highly latency sensitive. So these all devices continuously generate raw data such as signals, images, video, and telemetry. While moving to the next layer, that is the connectivity layer. So in this connectivity layer, we will see all the devices communicate through connectivity layer, which supports multiple protocols such as 5G, Wi-Fi 6, Bluetooth 5, LoRaWAN, Zigbee, and NB-IoT. So this multi-protocol approach ensures the universal connectivity and device flexibility and supports for both high bandwidth and low power devices. So as we come across the low power is the main revolutionary concept where the people will be interesting in going for low power. When moving to the next layer, I mean the edge and fog computing layer. So here actually we'll see the three intermediate intelligence layers, that is edge AI gateways. So in this edge AI gateways, it performs the local processing close to devices, and it will enable the ultra low latency less than 10 millisecond and real time interference and reduce cloud dependency. So when it comes to the fog computing nodes, these fog nodes act as an intermediate layer between edge and cloud. So they aggregate data from multiple devices and perform regional analytics and coordination. So when come to the mobile edge computing, so it actually supports high mobility and real-time applications such as um, connected vehicles and smart transportation. So the top layer is the cloud AI platform. This is actually responsible for model training, the big data analytics, and global optimization and orchestration. So this cloud provides unlimited scalability and advanced analytics and centralized model management. So this everything again we see something called hybrid intelligence concept. So this represents the hybrid AI model where the real time decisions happen at the edge and larger scale learning happens in the cloud, and fog nodes balances both workload and performance. So this ensures optimized performance, cost efficiency, and privacy protection and fault tolerance. So the key takeaway from this slide is that the modern IoT systems are no longer cloud only. So they are actually the distributed intelligence systems where AI runs across edge, fog, and cloud layers, enabling faster, smarter, and more reliable decision making. So with this, we will switch to the next slide. So here we can see the comparison between, we can now better understand why edge and cloud decisions are critical. So, and how this AML unlocks the values across different IoT applications. So this slide actually compares the edge AI and cloud AI, which is one of the most important design decisions when building AI-enabled IoT systems, that is AIoT systems. So when coming to the latency, the edge AI is preferred when the low latency is required, such as in autonomous vehicles, industrial safety systems, or medical monitoring. Because the data is processed locally, the cloud AI introduces high latency due to data transmission, but it is suitable only for non-time critical analytics. So for sensitive and or regulated data such as healthcare or surveillance footage, Edge AI is advantageous it uh, because the Edge AI's data does not need to leave the device. So we actually mean for local processing here. But the cloud AI, while powerful, but it requires strong security as well as the compliance controls. Why? Because to implement this cloud AI, we need to, meet the security cloud constraints. So without that, we cannot use for cloud AI. The edge AI requires to function when with intermittent or poor connectivity, whereas cloud AI heavily depends on stable network access. The complex model training and large-scale analytics are better handled in the cloud, while the interference and lightweight models run efficiently at the edge. So edge AI can reduce bandwidth and cloud compute cost, while the cloud AI benefits from economies of scale for centralized processing. See, the most real-world deployments use the hybrid model, where they meet. The real-time interference happens at the edge, and model training and long-term analytics occur in the cloud. So this improves the performance, reliability, and cost efficiency. So actually there is no one size fits all the requirements. I think we should use a combination of edge and cloud to satisfy our application requirements, and this will provide to deliver best results based on the hybrid architecture. So now let's move to the next slide, which is again the critical real world health domain. So as I said, the in the health domain, we need to expect the patient monitoring, remote patient. So this healthcare is one of the most important or impactful application areas of AML enabled IoT, where intelligent devices directly improve patient outcomes and reduce operational costs. The AI powered IoT devices continuously monitor vital signs such as heart rate, oxygen levels, and glucose levels. The machine learning models deployed for this patient care will analyze the data in real time to detect early warning signs, enabling proactive care and chronic disease management. The studies shows that the remote monitoring can result up to 30% reduction in hospital readmissions, which significantly lower healthcare costs and improve patient quality of life. So the AI model deployed for medical imaging such as X-rays, CT scans, and MRIs can achieve over 95% of diagnostic accuracy. So the real-time image analysis helps clinicians uh, to detect abnormalities faster, leading to 25% faster diagnosis. So examples include the intelligent insulin pumps, AI-enhanced pacemakers, and smart contact lenses that automatically adjust behavior based on the patient data. The overall AI-driven IoT solutions in healthcare have the potential to deliver 50%, $50 billion in cost savings through improved efficiency, early diagnosis, and reduced hospital stays. The combination of IoT data and AI intelligence enables predictive, personalized, and preventive healthcare rather than reactive treatment. So now we'll move to the next slide where we can see more about the return on investment analysis and business value based on the presentation. So in this slide, we can see that the slide focuses on the business justification by adopting AML in IoT systems by highlighting the measurable returns on investment and cost savings. So basically, the ROI based on the application area As you can see in the figure, the predictive maintenance shows the highest return. As I explained earlier, it is around 340% by preventing unexpected failures. The next, quality control delivers approximately 280% return on investment, reducing defects and rework. The energy optimization achieves around 220% return on investment through intelligent consumption management. And the security systems provide about 190% return on investment, improving the safety while reducing manual monitoring costs. So the organization typically experience 25 to 40% reduction in maintenance cost, 15 to 30% savings in energy consumption, and 50 to 90% reduction in quality defects. So the AIoT projects usually start with pilot implementations lasting 3 to 6 months. The payback period for most solutions falls between 18 to 36 months, making them financially attractive. So these numbers demonstrate that AML in IoT is not just a technology upgrade, it's a strategic investment with strong financial returns. So when implemented correctly, the AIoT solutions deliver both operational excellence and long-term business value. Next, we will dive into the industrial use case, the smart manufacturing and industrial IoT. So the manufacturing is one of the earliest and most successful adopters of AML-enabled IoT. Often we refer to as Industry 4.0. The AI models analyze sensor data such as vibration, temperature, and acoustics to prevent equipment failures before they occur. This results in approximately 25% cost reduction and up to 70% reduction in unplanned downtime. When it comes to quality control, the computer vision systems powered by deep learning inspect products at real time, achieving 99.9% defect detection accuracy. So this improves overall product quality by about 15% while minimizing the manual inspection. So the AI-driven energy optimization adjusts machine operations based on the demand, leading to around 20% cost reduction in energy savings. I mean energy management. So by combining the IoT data with the AI forecasting models, manufacturers can achieve up to 30% reduction in inventory levels while maintaining service quality. So these systems enable data-driven decision making, shifting manufacturing from reactive operations to predictive and autonomous processes. So the key takeaway will be the AML transforms factories into self-optimizing systems, improving efficiency, quality, and sustainability. So the beyond factories, like AI powered, is also reshaping urban environments. Let's explore smart cities next. So the smart cities use the AML enabled IoT systems to improve urban living by making cities more efficient, sustainable, and safer. The AI models analyze real time traffic data from cameras and sensors to optimize signal timings and traffic flow. So this can result up to 20% reduction in travel time and around 15% decrease in vehicle emissions. So this will improve the uh, safeguarding the environment by implementing this AIoT in terms of smart cities. And in terms of public safety, the AI-powered surveillance and emergency response system helps. I mean, it helps to detect the incidents faster, leading to 30% faster emergency response system. The IoT sensors combined with ML models monitor the air quality, the noise level, and waste management. So the predictive analytics helps city authorities to take proactive measures to address pollution and optimize resource usage early itself. So these systems enable city administrators to move from reactive governance to predictive and data-driven urban management. So the AI-driven AML-driven IoT solutions plays a critical role in building resilient and sustainable cities. So with this, we'll move to the next slide, which gives the how AML applied in precision agriculture. So the agriculture is increasingly adopting AML enabled IoT to address challenges such as water scarcity, the crop diseases, and productive demands. Especially in terms of crop monitoring, the IoT sensors and drones collect the data on soil moisture, temperature, and crop health. So the AI models analyze this data to detect diseases early and optimize crop growth, resulting in up to 20% increase in crop yield. The machine learning driven irrigation and fertilization systems enable 30% reduction in water usage and about 25% decrease in chemical consumption, improving sustainability. So the wearable IoT devices monitor animal health, its movement, and the feeding patterns. So the AI model deployed uh, for this segment will detect the early signs of illness and automate feeding schedules, improving the productivity and the animal welfare. So these technologies will help the farmers to make decisions, which is again the data-driven decisions and reducing the waste and increase the profitability. So the AI-powered precision agriculture enables the sustainable farming with higher efficiency and lower uh, environmental impact. So with this, we can move to next slide, which will tell about the most advanced AIoT applications in terms of autonomous vehicles, the future of transportation. So in this slide, we can see that the autonomous vehicles represent one of the most complex and safety critical applications of AML in IoT. So when it comes to the self-driving vehicles, where it really depend on multi-sensor fusion, combining data from various sensors and the lidar and radar and ultrasonic sensors. So the deep learning models will be deployed at this in terms of the model will process this data to achieve up to the 99% of perception accuracy. So the AI models perform the real-time decision making and path planning with latency often below less than 10 milliseconds, enabling safe navigation in dynamic environments. The AI-driven autonomous systems have the potential to reduce the road accidents by 40% and thereby representing nearly a 10x improvement in safety. The 10 times of improvement the safety compared to human only driving. The vehicles communicate with other vehicles and infrastructure to V2V and V2I communication, making them an integral part of IoT ecosystem. So the autonomous vehicles showcase the full power of Edge AI, where real-time intelligence, safety, and connectivity must work together seamlessly. So we can see there's the efficiency when compared to the human driving is um, lesser than the efficiency with autonomous driving. So the moving from the vehicles to homes, let's see how AML enabled IoT improves everyday living through smart home applications. So in this slide, we will see that the realistic, I mean, about the smart homes, they are one of the most visible and widely adopted applications of AML enabled IoT directly impacting the daily life. The AI-powered smart thermostats and energy management systems learn user behavior and adjust cooling, heating, and lighting automatically. So this results up to 30% energy savings while maintaining the comfort. So the AI-based surveillance systems use the computer vision to detect intrusions, recognizes faces, and identify the unusual activity in real time, significantly improving home security. The voice assistants and recommendation systems use machine learning to understand user preferences, enabling the personalized lighting, environment, and automation routines. So these systems offer convenience, cost savings, enhanced security, and improved quality of life. The smart homes demonstrate how AIoT brings intelligent automation into everyday environments, making technology more intuitive and responsive. So let's go deeper into the technical backbone of AML enabled IoT system architecture. So this slide provides a deeper technical view of how AML models are embedded and operationalized within an IoT system from data generation to the decision making. The architecture starts with the data acquisition from the device layer. So data acquisition from the device layer actually comes from the IoT devices and sensor devices, which may include the images, time series signals, or event data. So the before applying the machine learning, the raw data undergoes pre-processing such as noise removal, normalization, and feature extraction either at the edge or in the cloud. So the trained AI/ML models perform inference often at the edge layer to support real-time decision making like anomaly detection, classification, or prediction. The cloud layer supports model training, retraining, and large-scale analytics and performance monitoring to ensure the continuous improvement of deployment models. So the key aspect of this architecture is the feedback loop. So the wherever the new data is continuously used to refine and update the models and enabling the adaptive and learning systems. So this architecture enables the scalability, intelligence, and automation while balancing latency, cost, and data privacy. So the AML enabled IoT architecture it transforms the static systems to self-learning, I mean adaptive ecosystem. So with this architecture in place, now I will focus on types of machine learning models commonly used in IoT systems. So this slide highlights the key machine learning model types that are most commonly used in IoT applications. So depending on the nature of the data, the based on the data availability, and we are able to see the I mean the dividing of based on the data, it will be divided. For example, for image, right, we will go for computer vision. So for image and video data from cameras, the CNN, the convolutional neural networks are widely used. So these models enable tasks such as object detection, defect inspection, and medical imaging. So achieving around 94.5% accuracy in many deployments. So the when coming to the time series analysis, the IoT systems generate large volumes of sequential data such as temperature, vibration, and ECG signals. So these systems will deploy the LSTM network to well suit for this application and typically achieve around 89% prediction accuracy for forecasting and anomaly detection. So the optimization techniques, right? So since the devices have limited resources, so the models must be optimized using techniques like model compression, pruning, and 8-bit quantization. So these methods significantly reduce memory usage and power consumption while maintaining accuracy. So the lightweight versions of these models are deployed at the edge, while more complex model can be trained and refined in the cloud. So this is actually a combination of the cloud, edge and cloud, so that based on the hybrid concept, we can easily utilize the a combination of cloud and edge architectures here. So the choosing the right ML model and optimization strategy is essential for achieving the high accuracy, efficiency, and scalability in IoT systems. So next we will move into the ML models for IoT. So, so this slide basically gives us the entire end-to-end AML pipeline. So for a AML engineer, so he has to go the all the blocks of this AML pipeline to implement any kind of AML solutions on the IoT devices. So this slide actually represents the end-to-end AML pipeline, showing how raw data is transformed into a deployed, continuously improving machine learning model capable of high accuracy, low latency, and high throughput. So this pipeline begins with um, data collection, which is again the foundation of any AI system. So this data is sourced from uh, historical data sets for long-term learning and the real-time data streams for live inference and IoT sensors generating continuous signals. So the quality and diversity of collected data directly influence model accuracy, which in this the targets 95% or higher. The key message for this data collection: good models should start with good data. So while coming to the next block, building block of AML pipeline, so data processing. So the raw data cannot be used directly. So it must be pre-processed to ensure reliability. So this stage includes the validation to check data integrity, normalization to bring features to a common scale, and data cleaning to remove noise, duplicates, and missing values. The efficient pre-processing enables ultra low latency, typically below 100 milliseconds. The key message of this block is the pre-processing ensures the clean and consistent and fast data flow. So next block is the feature engineering. The feature engineering is where domain knowledge meets machine learning. The key steps include the feature extraction, I mean deriving the meaningful signals. Next, transformation, encoding, scaling, or aggregating the data here. The feature selection, I mean retaining only the most informative features here. So this stage actually optimizes overall system performance and supports high throughput handling 10K plus events per second. So the key message for this block will be the better features often matter more than complex models. So going for the next stage of the AML pipeline, which is nothing but the important of this model training. So in this model training, the once the features are ready, we will train the models using algorithm selection based on the problem and hyperparameter tuning to optimize the performance of the model to derive to getting the high efficiency and the cross validation to ensure the generalization across different models. Actually, this stage balances the accuracy, robustness, and scalability. The well-trained models help achieve uh, efficiency of 99.9% system uptime in production environments. So the key message here, training focuses on building reliable and generalizable models. So the last part of building block is deployment and monitoring. So here, after training, the models are deployed into production systems. So this stage includes the model deployment to edge or cloud. I mean, depending on our cost, I mean, based on the use case or cost usage, it can be deployed to edge or cloud, or it may use both for the business perspective. So the performance monitoring to detect the drift or degradation, and the updates to keep the models currently to updating based on the usage. So the monitoring ensures that the model remains accurate under all the real world conditions. So the deployment is not the end; it is actually the beginning of real learning. So that's the reason you can see the curve, which again goes for, but again the start after the top arc. Actually, the curved arrow at the top represents the continuous learning and model optimization. So whenever as the new data gets arrived here, the models are trained and features are refined and performance is continuously improved. So this is comes under a part of continuous integration and continuous deployment. So the modern AI systems must learn continuously, not once. Why? Because when the model gets trained, we have trained with the only the seen data. So what about the unseen data? So this will be again, which will be trained at later amount of time with the model and to improve the accuracy to get the predicted out from the model. So the key takeaway for this, it demonstrates how AI systems achieve high accuracy, low latency, high throughput, and near perfect uptime by carefully orchestrating each stage from data to deployment. So the understanding this pipeline helps us appreciate how AML integrates seamlessly with IoT, edge computing, and cloud platforms to deliver real-time intelligent applications. So with this, I am moving to the next slide where it we can talk about the edge computing platforms. So in the edge computing platforms, so this slide actually focuses on the hardware platforms that enable AML processing possibly directly at the edge of IoT systems. So unlike cloud servers, edge devices operate under strict constraints, limited power, memory, and compute. So yet they deliver real-time AI inference. So the platforms such as NVIDIA Jetson provide high performance AI acceleration ranging from 21 to 275 tops, suitable for vision-based robotic applications. Again, the Intel-based Intel Neural Compute Stick, which will enable the USB-based AI acceleration for existing systems. So the Google Coral, again, it's a part of Edge TPU, which is optimized for low latency, high efficiency interface. So, well, these are the high level of AI, how the hardware will be used. For example, if you want to implement the AI in microcontrollers, so for ultra low power applications, AI runs on microcontrollers like ARM Cortex M55 and STM32, consuming less than 1 watt of power. So these platforms actually support TinyML, I mean the tiny machine learning package, which enables the intelligence on battery powered devices. So the choice of edge platform again depends on application complexity, power budget, and latency requirements and cost constraints. So the edge computing platforms are definitely the foundation of real-time AIoT, which will be enabling the intelligence to run where the data is generated. So with the hardware in place, now the next slide will cover about the software frameworks and platforms used to implement AML in IoT systems. So these are the this slide actually highlights the software frameworks and platforms that enable the development, deployment, and management of AML models in IoT environments. When coming to the Edge AI framework, so are the Edge AI, so lightweight uh, frameworks such as TensorLite, PyTorch Mobile, and ONX runtime are widely used. So these frameworks are optimized for low latency, interference, and small memory footprint and hardware acceleration. So we'll going for the other frameworks where the cloud platforms are used, like platforms like AWS IoT with SageMaker, Azure IoT Central, and Google Cloud IoT provides actually the scalable model training and device management and data analytics and monitoring. So these platforms support the entire ML life cycle, including the model training, validation, deployment, and versioning of the various um, models and the rollback to whichever the model works perfect for particular AML system. So these tools actually mean for, the model compression, the optimization and over the air updates ensure that the models can be efficiently deployed and continuously improved across devices. So the successful AIoT implementation required the tight integration between edge and cloud frameworks. So often using standardized models like ONX runtime. So choosing the right combination of frameworks will actually simplifies our development and it improves the scalability and reduce operational complexity. So with that, we'll move into the next important critical aspect of AIoT systems. So here, so the this actually the slide, for the data, right? So we are actually getting data from various sources, right? So the and again, the data is the fuel of 21st century. So the data is the actually the backbone of AML IoT systems, and managing it securely and correctly is essential for system reliability and trust. We know that, right? For increasing AI on data, we may chance of getting this to, security compliances. Not following the security compliances. So in that case, actually, so the AI models are only as good as the data they receive, but real time data validation, noise filtering, and multi-fusion sensor fusion. So this will actually ensure the accurate and consistent inputs. So now to protect the data, we need to protect the sensitive information for that particular data. And many systems perform the edge-based processing, ensuring raw data do not leave the device. So the raw data stays in the device itself, and techniques such as differential privacy further reduce the leakage of further reduce the risk of data leakage. So in this one, the security mechanisms like the IoT systems must be protected against cyber threats using HSMs, hardware security models, and going for secure boot and device authentication and end-to-end encryption and for the data in transit under the rest. So the strong data governance helps organizations um, comply with the regulations such as GDPR and HIPAA and industry-specific standards. The effective data management and security are not optional. They are actually the foundational requirements for scalable and trustworthy IoT deployments. So as you can see that here the current minimum security value, so this can be much improved when we go for quantum step, which is nothing but again 4096 bits for the key for the particular security model. So despite these benefits, the AIoT system face several challenges. The next slide discusses the key challenges and practical solutions. So this slide actually provides us like when we are enabling the enable IoT offers significant benefits, and it also introduces technical and operational challenges that must be addressed for successful deployment. So the technical challenges here again, the IoT devices have the limited processing power and memory. So this is addressed using AI accelerators, specialized chips, and model compression techniques. So many IoT devices are battery powered. So energy efficiency is critical here. So to again here the low power hardware designs and optimized inference models help extend device lifetime. So the updating AI models deployed across thousands of devices can be difficult. So we actually plan for over the air updates to update through over the air. So here in this case, the over the air update enables the secure and scalable model upgrades. Uh, Again, the existing infrastructure may not be AI ready, right? So the API gateways and middleware allow seamless integration without replacing legacy systems. A shortage of AI and IoT expertise is a common issue here. So the organizations address this through training programs and cross-functional teams. The most AI IoT challenges are solvable with the right combination of technology, processors, and people. So next, we will look at the real-world case studies that demonstrate these concepts into actions. So this slide clearly, I mean, after understanding the architecture and applications of AI-enabled IoT, so this slide focuses on major challenges faced during IoT implementation and the strategic solutions used to address them. Here, these are the major challenges and these are the strategic solutions available. So let me explain each and each here how we can able to uh, apply the solution to for the challenge occur here. So let me start with security and privacy. So this is one of the biggest challenge in IoT is the security and privacy. So the IoT devices are often resource constrained and widely distributed, so making them vulnerable to data breaches and device level attacks. So to mitigate this, organization adopted a security framework that includes the end-to-end encryption, strong access control mechanisms, and secure authentication and authorization. So the key message here, security must be built in design, which should not be added later. It should start from the beginning itself. While moving in the next data management cloud integration, the here the IoT systems generate massive volumes of data at high speed and multiple formats. That is three V's: volume, velocity, and variety. Currently, we have five V's also, but right now for this current context, we'll talk about the three V's only. So the managing the data volume, velocity, and variety becomes a major challenge. The solution is to the cloud integration, so which provides the scalable storage and real-time analytics and centralized data management. The key message: the cloud should enables the uh, scalable and intelligent data handling. So the third major challenge here, connectivity issues. So the connectivity challenges include network reliability, bandwidth constraints, and latency issues. So for time-sensitive applications, sending all data to the cloud is not practical. The edge computing will address this one by processing the data locally first, then reducing the latency there and maintaining the functionality even during network disruptions. So the key message for this one, the edge computing ensures real-time responsiveness. Uh, Going for the next major challenge, the cost and return on investment based implementation. Here, the high initial investment and maintenance cost often raises concern about the return on investment. So the organizations mitigate this risk through phased implementation, where project starts with small pilots, then ROI is validated early and deployment scales gradually. The key message will be a phased approach which reduces the risk and improves return on investment. Going for the next major challenge, the integration and API standard, right? The integrating the IoT systems with solutions with legacy systems is another common challenge. So the different vendors and protocols often lead to compatibility issues. So the using the standardized APIs and protocols enables easily system integration easier and vendor interoperability and long-term scalability. So the key message should be the standard that should simplify the integration and future-proof systems. So while going for the next one, the skill gap and training program. So finally, many organizations face a skill gap in AML and IoT technologies. The lack of trained personnel can slow down and even derail projects. This is addressed with the training programs which focus on skill development, knowledge transfer, and building cross-functional expertise. So for this key message will be peoples and skills are as important as technology. The overall takeaway from this slide will be the every IoT challenge has a practical and proven solution. The successful IoT implementation requires a balanced approach across technology, processes, and people. So by addressing these challenges strategically, organization can scale a AML-enabled IoT systems confidentially and sustainably. So, so this slide basically tells us about the General Electric predictor. So this is a platform which has done the case study. So this case study illustrates how AML-enabled IoT delivers real large-scale business impact in an industrial environment. So the GE Predicts is an industrial IoT platform to monitor and analyze complex assets such as aircraft engines, turbines, and artificial and industrial machinery. So the platform monitors over 50,000 plus assets, processing more than 10 million data points per flight, demonstrating true enterprise scale AIoT deployment. So the core capabilities of this predict uses the digital twins to create virtual replicas of physical assets and predictive maintenance models to forecast the failures early and anomaly detection algorithms to identify abnormal behavior in real-time scenario. So the business results how they got. So these capabilities enable the 2 to 3 weeks of early failure warning, allowing proactive maintenance. As a result, so GE reports approximately uh, $1 billion in annual savings. And the strategic insight of this case study shows that the AML in IoT is not experimental; it is a mission critical revenue impacting technology. So as you can see the future trends of this AIoT, AML in IoT. So now we are in ultra low power. The next we are going for autonomous systems, then going for 6G integration, then quantum IoT, then digital twins finally. I mean the 2031 year onwards. So this slide looks ahead at the technologies that will define the next generation AML IoT systems. So the combination of the 5G and AI enables the ultra low latency, often below 1 millisecond, and it supports up to 1 million devices per square kilometer. So the features like network slicing ensures the reliable application specific performance. Uh, Neuromorphic computing. So this neuromorphic processors are brain inspired chips designed for highly efficient AI processing. So they can be up to 1,000 times more energy efficient making them ideal for future edge AI applications. The quantum ML processing in the quantum ML learning. So the quantum ML promises the exponential speed up for certain optimization and learning tasks. While still emerging, personal adoption is expected around 2028 to 2030. Explainable AI. So the explainable AI here, as AI decisions increasingly attract safety and compliance, the explainable AI becomes critical. The XAI enables transparent and interpretable decisions, supporting regulatory requirements and user trust. These explainable AI texts can be applied for medical field to for clinical representatives to decide the decisions more in a transparent manner. So these trends indicate the shift towards faster, more efficient, and more trustworthy AIoT systems. So with future technologies in mind, let's move to practical implementation roadmap for organizations. So these are this is the strategic implementation roadmap where we can show, this slide actually presents a phased roadmap uh, to help the organizations systematically adopt AML IoT, reducing the risk and at the same time maximizing its value. In the phase one assessment, the organization should assess existing IoT infrastructure, identifying the high impact use cases, and build cross-functional systems involving IT, data science, and business stakeholders. And this is the part of the phase one. Now coming to the phase two, during this phase, the selected use cases are implemented as pilot projects. This focuses on validating the return on investment, testing the feasibility, and establishing the MLOps pipelines for model deployment and monitoring. The phase three, it could be, 1 year to 2 years. The successful pilots are scaled into production systems. This includes setting up monitoring, retraining mechanism, security controls, and performance optimization. For the phase four, which is the final phase, the AIoT becomes a core enterprise capability, driving competitive differentiation, automation, and data-driven decision making across the organization. A phased approach ensures the controlled investment, faster learning, and sustainable scaling of AML IoT initiatives. So with this, we can move to the next slide where it tells about the best practices and success factors. So this slide summarizes the key best practices that constantly lead to the successful AML enabled IoT implementations. From a technical perspective, start with simple models and gradually add complexity. And again, the invest heavily in data quality and data governance. Use hybrid architectures to balance latency, cost, and scalability. So here the hybrid architectures refers to the a combination of edge and cloud AI platform. So the AIoT success is not just technical and it's organizational. The strong executable sponsorship is essential, and the cross-functional teams ensure alignment between business and technology. So the continuous upskilling and learning address to help address talent gaps. The business alignment again, clear value proportions and well-defined KPIs ensure AIoT initiatives stay aligned with business goals, and strategic ecosystem partnerships accelerate innovation and reduce time to market. So these are the part of business one. While coming to the risk management, again the security, privacy, and compliance must be built in from the day one. So it includes actually the security by design, regulatory compliance, and ongoing bias monitoring and model validation. The key takeaway here, the AIML enabled IoT projects succeed when technology, people, and strategy move together. So next we will see how AIoT contributes to broader goal sustainability. So this slide highlights how AIML enabled IoT contributes to sustainability goals, which are increasingly important for governments, industries, and organizations worldwide. The AI-driven IoT systems continuously monitor and optimize energy usage in buildings, factories, and cities, leading to significant reductions in energy consumption and carbon emissions. So, in areas such as management, water management, agriculture, and waste management, so the AI IoT enables precise resource usage, reducing waste and environmental impact. The IoT sensors combined with AI models help monitor air quality, water pollution, and climate conditions, and enabling early intervention and informed policy decisions. The AI IoT supports predictive maintenance and asset life cycle management, extending equipment life and reducing material waste. The AI/ML enabled IoT is a key enabler of sustainable data-driven decision making, balancing economic growth with environmental responsibility. So, with keeping this sustainability in mind, the final action-oriented slide, the next steps and call to action. This is given just for a reference, like how we can go for, implementing this AML across various organizations. So the first will tell us the immediate, 30 days. The organization should assess their existing IoT infrastructure and identify high impact AML use cases and form a cross-functional evaluation team. For the short-term goals, the next 90 days, select and launch a pilot project, choose technology and implementation partners, and begin prototype development and testing. For the medium-term objectives, within a year, implement and refine pilots, build internal AIoT capabilities, and develop production deployment plans. For the long-term vision, organizations should aim at AIoT solutions enterprise-wide. Achieve the competitive differentiation and enable data-driven business models. The key message is simple: start small, learn fast, and scale strategically. So with this, I'm completed the slides. So let me give the demo for this. A sample demo. First, we will see the IoT demo, how it looks. Then we will go for AML implemented in IoT, right? Give me 2 minutes time. I'll just make ready.
Okay.
Yes, yes.
Okay.
So I think we'll start with the IoT device, that is the optimized device, like Darshit
Yes.
explained earlier. Yeah.
Yes.
So
Yes.
we'll start with that simply. Then we'll go how the AML is applied in that area. Yeah. Will you able to see the screen? Mobile
Yes.
screen?
Yes.
Yeah. So this is an
One
optimized app.
No. Ek minute. Have you started?
Yeah, I started.
Yes,
sharing.
sir, it is visible.
Yes, visible.
Yeah. So the optimized app, which is developed by Xylem, Here is it is actually the works on Xamarin. Uh, so in this tool, in this app, we actually gives I mean the parameters what we collect from the device. As you can see, the device here, right? The optimized device. So this is
Optimize.
actually a condition monitoring device, which will give the various parameters like temperature, vibration, and we can connect even the pressure sensor externally. So this is I just uh, giving the demo to understand for a simple IoT device how we can deploy AML model. So here you can see that we can see the temperature for a period of time uh, from the condition monitoring asset. Basically, this device will mount on the motors or pumps to monitor the activity for the various parameters like temperature, vibration. So here the temperature you can see that, and moving to the vibration for the three axis X, Y, Z, it will report the vibration. Right now it is at desk, so you may not see the major changes here. It is very small changes. So we can see that the trend for all the three axes, and it has the battery also to just see how the battery consumption for this device. With this optimized device is again connected to a pressure sensor for an entire hydraulic application where we see the hydraulic uh, behavior, finding the pressure in the entire hydraulic application. For agricultural monitoring, right, for the heavy hydraulic, we can easily connect the pressure sensor to observe the pressure present in the valve. We can easily see the pressure. Right now it is at desk. You can see that it's showing 0 psi. Why? Because we haven't connected this to any system right now. So this is a part of an IoT demo, how it looks from the technology point of view, how the IoT device looks. So this is an example where we can see that now we can see that it actually syncing with the mobile app. Right, you can see that the sync activity with the round fashion. So it actually started syncing with the mobile app. So as you can see, the device is here. Now the mobile app is syncing with this device locally. Okay, and now it has completed the sync. Now we can see the latest timestamp, 8:41 p.m.
Yeah.
Right? Yeah, and you can see the latest data as well for the differential pressure and the suction and discharge. So this is basically a small example of IoT device. Now I will go ahead. Going for another demo, little demo where we can apply the AML on this data. So we have done the exercise and we got some, based on the data from this device, we applied some AML techniques and we implemented ready to demo, how we can showcase the AML model can be deployed to the, right now I have used for only the internal system. So let me just show you that. So this is actually, again, I am showing from React Native to easily demonstrate how we can show this demo. So this is again, we actually done the AML approach. As I explained earlier, from the entire pipeline of the AML, right? Starting from the data collection to the deployment. So now I have done all these steps and we deployed the model at the cloud, the locally. Okay, now using that cloud, we are able to understand like how we can predict the data. So let me show you some little demo. First we'll start with test API. So this is an API which gives then connectivity between the cloud and mobile device, right? Then we will go for the template. First we will go for sample data. So these are the sensor data. Actually, we have currently deployed only for vibration. So using the vibration, these are the 19 features. We actually done the training with the model, and model was deployed in the cloud. And using this model, we are actually predicting the outcome of the model based on the given data. So now we'll start with the sample data. So the sample data has been given through the mobile app. You can see the predicted it categories under unbalanced impeller. So this will actually demonstrate for the user based on the given data whether fault will happen or not. It is a kind of supervised classification. So now let me show you that another demo. How we can leverage this to, for the bulk amount of data. So let me add some data for this. I have added the 55 rows of data. I'm going for batch prediction, where you can see the batch prediction results as well lively. So now I fed the data to the model. The model is already deployed in the cloud. Now, based on the given data, model is predicting the fault. You can see that the 55 rows has been processed. The row one showing the normal mode. This is known data, but we try to show that it will easily identify the what type of failure it happened, like a seal failure, soft misalignment, and unbalanced impeller. And we seen that cavitation. So the cavitation also it shows. So this easily will predict the model. Performance with 95% performance, and it will usually showcase the what fault happened on the installed machine. For example, if this optimized device has installed on the machine, so based on the data coming from the device, we will usually predict the future the performance as well as predictive maintenance required for that system for the machine. So this will showcase like how the AML applied um, for the IoT device. So that ends the session. Do you have any queries I can answer?
Yes, participants, if you have any question, please either raise your hand or write in the chat box.
In renewable integrated microgrids, which is more effective to perform AI-based forecasting and optimization, edge AI or cloud AI?
In case of renewable energy, right?
Yes.
Yeah.
In renewable integrated microgrids.
Okay, integrated. Okay.
Hmm.
So in this one, actually for this one we can go for hybrid approach. Depends on the business case. Suppose if we go for the cost doesn't matter, then we can go for the cloud AI. Okay, if the cost matters, we can go for mixed approach. One is the edge AI, then again the combination of cloud AI. So for this particularly the grid, right? So we can go for how the model, like we can go for various regression models. For the linear, we can use random forest. We can use XGBoost, and we can the deployment should be maybe basically, as I said earlier, we can go for both approaches. We go for edge, or we go for fog also, we go for cloud also. Depends on the use case. For example, if you go for real-time control, right, we can go for edge. If you want to go long-term, forecasting and optimization, then we can go for cloud.
Yes. Any other question?
If any participants have any question, they can ask. I hope you all are live or sleep.
Okay. Okay. I believe there is no question from participants. Yeah. One question is there, sir. What
Yeah.
practical limitations arise when scaling AI-based IoT solutions from a laboratory microgrid to a real distribution level microgrid?
Can you repeat, sir?
What practical limitations arise when scaling AI-based IoT solutions from a laboratory microgrid to a real distribution level microgrid? Sir, it is in the
So
chat box if you can.
yeah, let me.
AI model to replace SCADA and DCS.
So for this special case, I think we will have something, the data and the sensing limitations. So when we talk about the lab, particularly with lab, we actually go for, I mean, the clean, the synchronized high resolution data, right? So in that perspective, while moving this to the real microgrid, we'll see the noisy and delayed sensor data in terms of the moving microgrid. So here the impact on A will be like the model accuracy will degrade, uh, and it will go for, I mean, the increased false alarms and unstable predictions. So here I think the scalability should be seen. I mean, if we go for lab, I think the high bandwidth and low latency LAN should be used. And here also again the real-time control becomes unreliable. So the model what we use for there was many things are there, so we can easily select based on the approach in moving from lab to the real time. I mean, depends on the use case again, the regulatory safety compliance and the interoperability legacy systems. So those things need to be checked to exactly how we can. But there will be something, the lab driven trained models fail in unseen conditions. That's for sure. But we need to see the use case, especially to power grid, how we can do the application of AML in that. But for that, there again, the utilities, right? It will be like a black box AI again for in terms of that. So we need to check for use case by case, how it will be applied there.
Any AI model to replace the SCADA and DCS?
In that case, so there is no AI model that can replace. Why? Because those are the local AI,
Supervisor.
right? For example, the SCADA is specifically for the deterministic control system, right? It actually
Exactly.
gives the real-time monitoring, and
Hmm.
again, it depends on the hardware monitoring. So actually, the platform, right? Where we configure the inputs and outputs for the particular system, it's been in the realistic manner. But it again, we need to check for the which hardware we are going to use. But we can go for backnet. Again, backnet again it depends on again the hardware dependent.
Exactly.
So
Exactly.
yeah, why? Because the backnet again it comes under
Mhm.
same use case. So the building automation control nets, right? So there again, the practical reality means I think we need to see. I mean, uh, how a layer is used in between. to go for efficient utilization of SCADA data. I mean SCADA implementation, right? I mean there we can use that AI, but we cannot replace that. That's the challenge here.
Yes, when we have certain or clear-cut rule-based something which is like if this is the threshold and more than that is
Mm.
not allowed, something like that, then we don't need AI, right?
Yeah, correct. Why? Because it is
Yeah. When we have
deterministic, right? Yeah,
deterministic, right? Exactly.
deterministic. Why? Because we know we expect the output, but we can
Yeah,
play
exactly.
with the data. I mean, how we want to showcase that data on the high level. So that
Right.
research we can do using AI. I
Mm.
mean, we can feed the data to backend. Then from the
Yeah,
backend,
and
we
then
can
we can.
implement the AI model there to showcase that.
Exactly.
The efficiency of that SCADA data. Yeah.
One more question. Is IoT
Power quality enhancement in microgrid and
uh,
renewable.
renewable
Yes, it can be
sources,
used.
particularly in monitoring and predictive analysis?
Okay. Yeah, actually, for getting approval of the power quality, we can deploy the model. Okay, but again, we need to see the specific use case. But basically, if you are trying to deploy the IoT, it's actually widely used for power quality and microgrid monitoring and the prediction. But again, with the clear practical boundaries, what we need to see. So we can see something, the typical IoT setup for this will be the smart meters, right? The smart meters data can be pulled to the edge gateway where the MQTT protocol is used. And again, through the MQTT gateway, we can easily integrate to the cloud. And from the cloud, we'll pull the AI analytics, how the prediction will be there. So
Mm.
that we can use it. I mean, if we want to deploy IoT, definitely we can improve the quality of the power. But we have to, I mean, look into the use cases like the case studies related to that particular environment. For example, to make the IoT enabled for grid, right? Again, we need to what type of data we need to use for the gateway to uh, pull the data, right? And that should be sent to the cloud. Now the cloud will actually the AML implementation will be, I mean, deployed on the cloud to give the AI analytics and its prediction. I mean, whether we have saved the power and whatever the storage, associated of the storage and load demand to the voltage and current frequency. So those things will be easily come across. I mean, we can use the protocols like MQTT, Modbus
But sir, in
for
that
this.
case, I think, sir, it will be very slow in that case, right? Power quality, I believe that the transient changes cannot be captured by cloud because it becomes very slow compared to the power quality changes, which are
Yeah.
the frequencies are in terms of gigahertz generally, or maybe kilohertz or when megahertz for the
Mhm.
transients. Uh,
Yes, yes,
uh,
correct, sir. But
so
here,
I think it's the
I mean,
application, right?
yeah, yeah, correct. It will not reach it. Correct, correct. You're right.
Yes,
So,
yes.
but again, we want to improve the, I mean, the feedback of these, I mean, the outputs from the meters, right? So
Right.
that we
Those
can be
things can be
analyzed,
right, right, correct.
analyzed. Correct. Yeah.
What about security and privacy concern?
In which area, sir?
What is the question, sir?
Ketan, uh,
Ketan Kumar said.
Ketan Kumar said, what about the security and privacy concern?
In I mean, again, the domain it matters.
Yeah, please
So
elaborate the question.
Uh, you may ask, please ask directly. If
Okay.
you
Raise your
want
hand,
to.
please.
Raise your hand. Ketan Kumar said. Yes, please. I think.
So when we see about the security and privacy concerns in basically
Yes,
in
yes.
IoT,
Yeah, Mitesh, please unmute. Ketan Kumar said.
Okay, sir.
Uh,
so which areas, sir? Or I will tell only the common.
Done, sir.
yes, please. Ketan Kumar said.
Yes, sir.
Yes. Okay.
Microphone was disabled. Setting.
Okay.
No,
Okay.
you're audible. You're audible. Please.
Audible.
So, my question is how the system will be secure after implementing this application of AI and ML in IoT device.
Okay. So in this one, I mean, depends on the use case. Basically, again, when we are implementing the AIoT, right, for specifically for this environment, we actually see the concerns in IoT. For example, there will be three based on the threats. We can classify the data. So first, we'll take the device level threats, the firmware modification, okay, and the insecure boot process, right? Next, network level threats. I mean, man in the middle attacks and replay attacks. So these things will be there, and again, data and application threats. So in this one, again, the API abuse or data poisoning. I mean, someone will be able to interference with the data. So these things will be secured layer by layer. For example, for a device security, we can go for a secure boot. I already implemented it one of the model, secure boot for the devices. So this will help us, maintaining the security and the communication between the device and whatever it communicates to outer layer. For example, let's take the app. If someone taps in between, right, it will be in the encrypted format. So once we implement, right, so it will increase the the security in that. That is one thing, and we can disable the unused port for the hardware also to stop doing this activity. And while coming to the network security, I think we can go for something, the end-to-end encryption, and we can go for firewalls also to strengthen its security. And at least, we can use something, the encryption AES 256. Like I told you, right, we can go up to AES 4096 also for quantum safe. So there also we can use the encryption at rest, and even encryption during transmission also we can maintain. And one more thing is to avoid these things. I think we should go for the for example, if we want to deploy A right in the for this particular microgrids or in normal one, we should see the data, what we use the data for modeling. I mean, for modeling the model, right? For learning the model, so generalization of the model. So those things also will come into picture. But we can maintain the standard practices like following ISO and IEC 27001 IoT security, right?
Yes. Yes.
And so communication TLS, the DTLS. So those techniques will be is coming as a part of the model, right? For this.
Sir, another query arise. I think that IoT device have some limited processing power. That I think. So how
Okay.
the complexity of the AI and ML algorithms will be efficiently used?
Okay. Limited processing in the sense, again, here, if we are going for low power, there will be definitely the limited power, limited
Okay.
processing power. Why? Because the low power devices will be working on, under 5 volt, right? So in that case, the IoT devices will be part of limited processing power. So as the question comes arise again, basically, I agree. Some of the models will not run. For example, if we want to deploy deep CNN or transformer or LSTM models, so it will be too large for the processor to process the data. So in that case, I think we can use something, TinyML package. For example, if you go for ARM, right? ARM, Cortex, any of the chip. So they have already the TinyML package available in the market. We try to see the equivalent, based on our specific constraints, we need to adopt that model, proprietary model, our own model. So then this actually TinyML will be given, gives us the chance to change as per our requirement based on the input, what we want to process, what we want to define that. So this can be overcome on that. I agree, but low power, but high power it doesn't. Why? Because the TinyML on that is actually the on-device AI that itself acts as a AI. But to avoid that, we can do one thing. We can go for local processing of data from the device, and we can deploy the model on the cloud. Let's do the interaction between the cloud and edge, so that we will build the model on the cloud and we can easily get the data. Instead of I have done same case like that.
Okay, thank you. Very nice, sir.
Clouds
Yeah.
have lots of resources, right? Azure
Yeah, it
and
has lot of resources. Yes, correct.
yeah.
Yes,
Sir, please turn on your camera, sir.
Yeah.
If possible.
Yeah. Yeah.
Sir, Ketan, sir, please, you can.
Yes.
Oh,
Yes.
We'll take one.
Network issue in my house.
click.
Yes, sir.
Oh, just to take a snap.
Yes, sir. Remarkable session. This
Okay.
session was remarkable.
Okay, sir. Thank you.
Okay, thank you.